All right, guys. Good evening, everyone. Please, if you are active, indicate that you are active so we can start. If you are active, indicate that you are active. If you are active, please indicate that you are active. Please, if you are active, indicate that you are active. If you are active, indicate your presence that you are active. If you're active, please indicate. All right, so guys, we shall start. Others should join us as we proceed, all right? So let's start. In today's class, we shall be looking at DC and instruments. DC simply means direct current and instruments. Under this topic, we shall be considering an introduction to DC introduction. We shall be considering the terms, some terms used in DC. Then we shall be considering what we call resistors in series and parallel. We shall be looking at analysis of complex circuits. Analysis, okay, of simple circuit first. Simple circuit. Then also analysis of complex circuits. Then this will lead us to the introduction of a law called Kirchhoff's law. Okay. At the end of today's class, every student in this platform, in this online class, should be able to understand what is a DC, some terms used in DC, resistors and in series and in parallel, how to analyze a simple circuit using Ohm's law, then how to analyze a complex circuit using the Kirchhoff's law. This will be our activities for today. So everyone should please pay attention. Now let's start with what is a DC? What is a DC? DC simply means direct currents. It means direct currents. Direct simply means is a current that flows in one direction. Unlike AC, AC is a current that flows in different directions. All right. You know, in the previous lecture, we talked about current electricity. When we talk about the flow of electric charge through a conductor, I will say that electric current can be grouped into two. One of them we say we have what we call static charges, right? And we have what we call current electricity. Static charge simply means a charge at rest, not in motion. Then when it comes to current electricity, we talk about charges in motion. Then under current electricity, we have what we call direct current and alternating currents. Direct current simply means DC. All right, we have undercurrent electricity. Undercurrent electricity, we say that current can either be what? DC or AC. In today's class, our emphasis will be on DC. DC simply means direct current. From the word direct, it simply means this is a current that flows in one direction. All right. AC simply means current that flows in different directions. My emphasis will be on direct currents. So when you hear the word DC, it simply means that current that flows in one direction. Okay, a good example of DC source is battery. All batteries, whether it's car battery, whether it's removed battery, all right, any form of battery have what we call direct current source. So all batteries are a good example of what? Of DC. All right. Number two, we have solar cells. Solar cells are also good examples of what? Of direct current. All right. We also know for other batteries, we have what we call removed battery. Removed battery also has what we call direct current. That is why if you have to put on your TV, if you don't put the remotes parallel perpendicular to the wall, to the TV, it will never work. If you place your remote up and you want to switch on a TV, definitely it won't work, because the current that is being stored in the remote battery is what? A direct current, meaning a current that flows in one direction. It must be directional, it must be in one direction. All right. So we have solar cells. Another examples of DC source is what we call direct DC generators. DC generators. All right. So these are the sources or examples of what? Of DC. We have all batteries, whether it's car battery, whether it's remote battery, whether it's radio battery, any form of battery you can lay hold on has what we call direct current source. Then the solar cells, like the solar panels, makes use of what? Direct current. Then we have our DC generators. These are sources of what? Of direct current. We also have what we call AC generators, which is the generators we all make use of, right? One thing you should know about AC is that it's a current that flows in different direction. Now, what is the graph of a direct current? How does a direct current look like? The graph looks like. Don't forget that, recall that charge is equals to what? IT. From here, our current is equals to charge over what? Time. Right? That means to find current, I have to differentiate charge with respect to what? Time. Charge with respect to time. When you differentiate charge with respect to time, the result is current. Are you there? This current can either be direct current or alternating current. One thing we should just know is that current simply means the flow of electric charge for one point to what? Another, right? For one point to another. When there's a flow of electrical charge or charge, we call that what? Current. And this current can either be direct, that flows in one direction, or can be what? Alternating, that flows in different what? Direction. So just know that current is equals to charge over what? Time. That means that if you look at this, current is directly proportional to charge, while current is inversely proportional to what? Time. That means current and charge are equivalent, but current and time are negative to each other. Meaning that if I'm to increase my charge, I have to increase my current. If the current increase, the charge must also what? Decrease. Are you there? But current and time are negative to each other. Now that means that if I'm to plot a graph of current or voltage against time, for a DC graph, if the current is DC, the graph looks exactly like this. What do you notice here? This is a straight line graph. This graph is parallel to the what? Horizontal what? Axis. Unlike a normal graph, that if I have a normal graph, if I have a graph of, let's say, normal graph, let's say, let me use V against I. That is the Ohm's law, right? This graph starts from the origin, right? A graph of voltage in volts, against current in amp is a graph that starts from the origin. This kind of graph has its 0 points, has its maximum points, right? But when it comes to DC, a graph of current against time, there is no maximum point, there's no minimum point, there's no 0 point. But when it comes to alternating current, is a current that flows in different direction. If I'm to plot a graph of currents against time in seconds, for alternating currents, this graph will look like this. Are you there? So this is for AC. This is for what? For DC. In the exam, they might just ask you to plot a graph or show a graph, show an AC graph or show a DC graph. Draw a sketch showing a DC graph. This is a sketch showing what? A DC graph. This is a sketch showing what? AC graph. What do you notice here? In an AC graph, we have the maximum, the peak current, right? We have the minimum. We have 0 points. We have 0 points. Are you getting the concept here? But in a DC graph, there's no 0 point, there's no maximum point, there's no minimum point. All the values of current are just the same. They are just the same. They are just the same. Okay? Meaning that irrespective of the fact that we have time here, as the time increases, it does not affect the change in what? In current or in voltage. If my time increased by 2, by 3, by 4, let's say by 5, by 6, by 8, as the time is increasing, the current remains what? The same. So we call that a steady and direct current. It is steady and it is direct. So this is a graph of a DC. Okay, let me take us through another journey. Now we have seen the sources of direct current. The sources of direct current, we have seen it. We have seen that. I want to take us through a journey. Derivation or derivative of what? Of charge. Of charge. With respect to what? To time. I've already stated that current is equals to what? Charge, right? Charge over what? Over time. Meaning, if we should differentiate charge with respect to time, that will give us what? Current. Differentiation of what? Of charge with respect to time equals current in ampere. Meaning the derivative of charge with respect to time equals what? Equals current. So when you plot a graph of charge against time, we have a current, right? That's what this means. Now, if the derivative of charge with respect to time equals to current, that means the integration of current will give us what? Charge. Integration simply means the reverse of what? Differentiation. In most questions, they might just give you current function with respect to time, and they will say find the charge. If you are given current function and we also find charge, what do? We have to integrate current to find charge. But if we are given charge function with respect to time and they say find current, what do? We differentiate. This is what I'm trying to analyze here. Let me show us. So if I'm saying that current is equals to dq over dt, meaning differentiating charge with respect to time equals to current. Let's look at the reverse of this. How do we get the reverse? I have to cross multiply. By the time we cross multiply this will give us dq equals to I dt, meaning dq times 1 equals to current times the T, which is what we have here. So integrating both sides. To find Q, I have to integrate both sides. I have to integrate both sides. By the time we integrate both sides, integral of the Q is equal to integral of I dt. All right. So integration of the Q is equals to Q equals to integral of I d what? I dt. There's a question from IMSU textbook. I'll be using this expression to solve with time. Whenever you are giving your charge function with respect to time and they say find current, just differentiate, like I just showed us, that when you differentiate your charge with respect to time, what we have here, we have current. Differentiation and integration are just reverse. Integration means the reverse of differentiation. So that means that if differentiating charge will give us current, that means integrating current will give us what? Charge, which is what I just expressed here. And how do we prove that? We have to cross multiply this expression, meaning the Q equals to what? I dt, right? Then apply the principle of integration. We have to integrate both sides. By the time we integrate both sides, that means integral of the Q equals to integral of I dt. Integrating the Q will give us Q. In integration, anytime you integrate a function, let's say dw, the result is w. Integrating the x, the result is x. Integrating the v, the result is v. So if I'm to integrate the q, what do we have? We have q. Integral of I dt. Are you there? Of I dt. Okay. So this is it here. This is the expression here. So this simply shows that when you integrate current, integral of current with respect to time will give us what here? Charge. I will come back to this. Just take note of these two expressions. We'll come back to this. All right. By the time we start solving IMSU and textbooks, the exercise and past questions, I'm going to apply this principle together. But I want to believe that we all know what is differentiation and integration. If you don't know the principle of differentiation and integration, please go through my previous classes. Just search my videos, or you can type differentiation by EMI-BRAIN. All right, you will see many videos I've done on differentiation and integration. It will really help you. Okay, but let's proceed. Let's proceed. The next thing I want us to look at is what we call arrangement of resistors. Resistors in series and what? And parallel. We shall consider a simple circuit and complex circuits. We shall consider two different circuits, simple and complex circuits. Please, if you are active online, indicate that you are active. Please, if you are active, indicate that you are active. Please indicate that you are active. Indicate that you are active. Please, if you have joined us, just click on the like button. Let me know that you are active. Click on the like button. Share the link to your classmates now. Let's start sharing the link. Let's start sharing the link. Don't just be active and yet we are not doing anything. Please, if you're active, indicate that you are active. Yes, Michael, I can see you. Michael is active. Michael is active. Please, if you're active, indicate that you are active. Please, if you're active, just like the button, click on the like button rather. Click on the like button, just be active, indicate in the comment section. Share the link to your classmates. Let them join this class. Okay? Let them join, let them join, let them join. Okay? All right. Now let's look at how to analyze a circuit. In a circuit, we can have resistors connected in series and also connected in parallel. All right? What's a resistor? A resistor is a device. The job of a resistor is just to oppose the flow of what? Of current. It gives resistance to the flow of current. All right? When the resistance that occur in a circuit, all right, is offered by a resistor, all right, we call that a resistive or reactance. Okay, but the job of a resistor is to resist the flow of currents. So we can have a circuit where our resistors are connected in series and what? In parallel. So the first is to analyze a series connection. Series connection of resistors. Connection of resistors. Series connection of resistors. Now, when I say series connection, when resistors are connected end to end, like this, we call this a series connection. All right? Here we have resistor 1, we have resistor 2, we have resistor 3. Another way of representing a resistor is this way. You can also represent a resistor in this pattern. This is also a resistor arrangement in series. Resistor 1, resistor 2, and resistor 3. Now listen, whenever resistors are connected in series, like they are connected end to end, two things happen. The first is that the same current flows through the resistor. Meaning, if I have 2 amp of currents flowing through this resistor, this same current that flows through R1 must pass through R2, must pass through what? R3, must pass through. All right? Even if I have 5 ampere, the same current must have to flow through the resistor. But something happened. Number 2 is that the potential drop is not the same. Same current, but there's a splitting of potential difference or different PED across what? Across each resistor. Two things we say that happen. Same current flows through each of these resistors, but in each of the resistors we have different potential drop, different PED across each word resistors for a series connection. Now I want to show us something very important. If we are saying that the same current flows through the resistors, so let's consider a circuit that has just 2 resistors. We have just R1 and what? And R2. We are looking at the circuit that has just 2 resistors connected in what? In series. Resistor 1 and resistor 2, right? Either in this pattern or in this pattern. We are saying that the same current flows through. Then my total current should be equals to what? I1 equals to what? I2. That's what that means. The current that flows through resistor 1 is the same current that flows to resistor 2. So total current, which is our 2 ampere, it can be 2, it can be 3, I'm just giving an instance, is equals to the current that flows through the first resistor equals to the current that flows through the second resistor. This is my first expression. Since we are saying that they have different PED or potential difference across each resistor, there's a potential drop. The potential drop across R1 and R2 are not the same. So that means that the total voltage in a circuit arranged in series will be V equals to V1 plus what? V2 plus what? Plus V3. What we are saying here is that the sum of the PD in resistor 1 plus that of resistor 2 must amount to what? The total voltage. Let's say, for example, if the voltage source is 24, let's say 20 volts, all right? As the voltage is coming, they will split. Maybe R1 might take 15 volts, then R2 will take 5 volts. But at the end of the day, when you add up the PD in R2 and R1, it must give you the total voltage of the circuit, right? Of the circuit. Okay, so that means that, yeah, we are saying that the current that flows through series connection of resistors, they are the same across each of the resistors, but the potential difference are not the same. So to get the total PD, we have to sum up. Since we are considering R1 and R2, it means I have to remove this from the equation. All right, but recall that V is equals to what? IR. If V is equals to IR, let's call this equation 2. If V is equals to IR, equation 3, what do? I can put equation 3 into equation 1, meaning anywhere I see V, I will replace with what? IR. Since the same current flows through, we can say that this becomes IR equals to I1 R1 plus I2 R2. I replace my V with IR. Since V is IR, so V1 becomes I1 R1 plus V2 becomes I2 R2. Since the current are the same, here will be IR equals to I R1 plus I R2. Since we are dealing with the same current, that I1 and I2 is equals to what? I. So here we can factorize this. Here we have IR equals to, what is common here is I. In bracket, we have R1 plus what? R2. Okay, from here, I can go with I. So here we have our resistance equivalent, meaning the total sum of the resistance in a series connection will be what? Yeah, be equals to what? R1 plus what? Plus R2. Okay, so for resistors in series, to find the equivalent resistance, we have to just sum up the two resistors, which is R1 plus what? R2. Suppose we have a diagram like this. Suppose we have a diagram like this. Let's say this is 5 ohms. This is 6 ohms. And we also find R equivalent. R what? Equivalent. So what do we do here? Is just to sum up. So my R equivalent, let's call this R1 and this what? R2. What will be our R equivalent? Is R1 plus what? Plus R2. So our R equivalent will be what? What's the R1 here? 5 plus what? What's the R2? 6. That will give us 11 what? Ohms. So the total resistance is 11 ohms. So let's look at parallel connection. Parallel connection. Please, if you are following, indicate that you are following. For parallel connection, of resistors, if I have parallel connection, like this, okay, parallel simply means when resistors are connected side by side, right? Side by side, whereby the branch of each of the resistors that connects the node, I have a node here, I have a node here. When two resistors are connected with their nodes, here we have resistor 1, R1, here we have what? R2. This is side by side. This is not end to end, right? So a series simply means end to end, just like this. Are we seeing it? I have resistor 1, resistor 2 along the same line, all right? What if I have something like this? Okay, let's analyze this circuit. If I have a cell here, a cell, and I have a resistor here, another resistor here. Let's say another what? Resistor here. Okay. Then let's say this is 2 ohms. This is 1 ohms. This is 3 ohms. All right. Let's call this R1. This R2. This R3. This resistor R1, R2, and R3 are in series. They are still connected end to end. If you look at it, I have a beginning, I have an end. A beginning, I have what? An end. They are connected and there's no node. I have a node there that separates R1 and R2 together. I have 2 nodes there. I have 2 nodes there, right? Okay. Or we can say we have a loop or a junction, right? We have a junction. We have it is a junction. This is a junction. I have a node. I have a node. So for this kind of diagram, we call this parallel arrangement. But for this, whereby each of the resistors are connected end to end is called what? Series what? Arrangement. So for this, to find my R equivalent is simply to add up R1 plus what? R2 plus what? R3. And that will give us what here? R1 is 2 plus R2 is 3 plus R3 is what? Is 1. So 2 plus 3 is 5 plus 1 is give us 6 ohm resistor. So our R equivalent for this kind of circuit is 6 ohm because R1, R2, and R3, they are all connected in what? In series. But if I have a diagram like this, like I've already explained, this is called parallel connection. Now, don't forget that we say that under series connection, 2 things happen. The same current flows through the circuit, but the circuit happens to have different potential drop across each of the resistors, right? Now, the reverse is the case here. Under parallel connection, we have different currents flows, all right? Okay, I have a current that flows here. This is I1. I can also have a current that flows this way, which is what? I2. Definitely, as long as we have a junction here, there's a current that flows through this way. This current here and this current are not the same. So for parallel connection, different current flows through each of the resistor, right? But we have the same potential drop. We have the same PED across each what? Each resistors. Across each resistors. We have different flow of current across each of the resistor, but we have the same PED. Just like the reverse of series arrangement. You have to take note of this. Now let's derive the expression for parallel connection. Don't forget that to find our R equivalent for series, what do? We just have to sum up, right? We have to sum up. But for parallel connection, let's see what we are going to generate here for parallel connection. For parallel connection, if I have R1 and I have here to be R2, okay, already we say that the same PED, right? The same PED, meaning V equals to V1 equals to what? V2. Let's call this equation 1. Then we say different currents, meaning that total current that flows through this circuit will be sum of the current that flows through R1, which is I1, plus the sum of the current that flows through what? I2. So to find the total current, I have to add up I1 plus what? I2. I1 plus what? I2. Equation what is this? Equation 2. But V is equals to what? IR. V equals to IR. Now let's find the value of the current here. I have to divide both sides by I. But I hope we are aware, by the time we divide both sides by what? By R, this will give us what here? I equals to V over R. Let me bring it out here again. Here we are saying that, okay, here we are saying that I rather, current is equals to V over R. V over R. Okay. Now, what do we do here? I have to replace this, just like we did in the first, which is series connection, where we derived formula for R equivalent. Let's see what will be the value of our R equivalent, resistance equivalent for parallel connection. What would that be? From I equals to V over R, right? This will give us I equals to, okay, let me repeat this. From I equals to I1 plus what? Plus I2, right? What do we say is our I? Is V over R. All right? That will give us equals to what? We are saying that the same voltage across each of the resistor. So for I1, I'm going to have here to be V1 over what? R1, right? I equals to V over R. So for this I, we have V over I. For I1, we have V1 over what? R1. For I2, we're going to have V2 over what? Over I2. But since the voltage are the same, this will be what? V over R equals to V over what? R1 plus V over what? Over R2. So this is R2, right? Over R2. Now let's go. Here we have, okay, V over R equals to, what is common here? I can factor out V. In brackets, what will remain here will be 1 over what? R1 plus 1 over what? R2, right? V is the same. I have to factor it out. When you multiply V by 1 over R1, I will fall back to this. Multiply V by 1 over R2, I will still fall back to this. So V is common. So this like saying V over 1, right? V can cancel out V here. We are left with 1 over R equivalent equals to 1 over what? R1 plus 1 over what? R2. Okay, all right. This is how to find our equivalent for parallel connection. Alternatively, I can also say this is same as our equivalent equals to 1 over what? R1 plus 1 over R2, all to the power of minus 1. All right? Yeah. Or we can also say that our equivalent equals to, yeah, what is common here is R1 times R2. When you divide this by this, R1 will cancel R2. That means R2 will remain. So R2 times 1 will give us what here? R2. Divide R2 by R2. R2 will cancel R2. We are left with R1. R1 times 1 will give us what? That's plus what here? R1. All right? Minus 1. Okay. So we can say that our equivalent is simply R1 times R2 divided by R2 plus what? R1. Or we can say our equivalent equals to R1 times R2 divided by R1 plus what? Plus R2. So any of this expression you would love to use can work for our equivalent. But for me, I prefer this or this last one. So we have 1 over R1 plus 1 over R2 all to the power of minus 1. When we evaluate further, that will give us this. So this is how to find R equivalent for a parallel connection of resistors. Now let's see how we can solve some problems from your textbook. Okay, a minute. From your textbook, this is the same textbook for both UNN students and IMSU students. So please take note. If you are a UNN student in this platform, please take note, okay? Take note. All right, let's look at this question that says, Okay, we have a question that says 3 resistors, 2 ohms, 6 ohms, and 9 ohms are connected in series. All right. I repeat again, 3 resistors, 2 ohms, 6 ohms, and 9 ohms are connected in series, and a 120 voltage battery connected across the combination. We are told that 3 resistors, 2 ohms, right, 6 ohms, and 9 ohms are connected in series, right? And the voltage across each of the resistors, okay, the voltage was given, the battery was given as 120 volts battery, all right? And we are asked to calculate question 1, find the equivalent, RO equivalent. Question B says, find the current that flows in each resistor, the current that flows in each resistor. Now, to solve this, you can decide to draw your circuits. Just bring out your battery source here. We are given that the voltage is 120 volts, right? I've already taught us how to draw a simple circuit. So what's the first resistor? We have 2. We have the next one, which is 6. We have the third one, which is 9, right? Connected. They are connected end to end. So we have 2 ohm, we have 6 ohms, and we have 9 ohms. Let's call this R1. This is R2. And this is R3. All right? All right, sorry. I just have to. So we have our R1, R2, and R3, right? Connected in series. So we have to find our equivalent. The first one says find our equivalent, which is R1 plus what? R2 plus what? R3. So this will give us our equivalent equals to R1 is 2, plus R2 is 6, plus R3 is 9, right? Okay. So by the time we add up this, it gives us 17 ohms. 17 ohms. 9 plus 6 is 15. 15 plus 2 is 17. So the R equivalent in this simple circuit is 17 ohms. The next is to find the current that flows through the resistor. Don't forget that we say that when resistors are connected in series, what happens is that they have the same what? The same current, right? And they have different what? Different PED. Different PED. Okay. Well, since the question says, let's find our R equivalent and the current that flows. We have gotten our R equivalent at 17. The next is to find our current that flows through each of these resistors. So we have our I1 current here, right? Here we have I1. Here we have I2. Here we have I3. Okay, so let's go. But recall that V is equals to what? IR. From here, we can get our current as V over what? R equivalent. So current becomes what? Our voltage is 120. 120 divided by 17. 120 divided by 17 will give us, divided by 17, will give us about 7.059. ampere. All right. Therefore, since R1, R2, R3 are in series, therefore we are saying that I is equals to what? I1 equals to what? I2 equals to what? I3 equals to 7.059 ampere. Therefore, my I1 is 7.059 ampere. Likewise, I2 is 7.059 ampere. Likewise, I3 is 7.059 ampere. Okay, so the same current must flow through each of the resistor. Okay, we have solved that. Let's look at the next question. The next question. All right. So the next question says that 3 resistors are connected in parallel. 3 resistors, which is 2 ohms, 6 ohms, and 9 ohms, are connected in parallel. All right. And a 120-volt battery. I guess it's the same question. 120 volts battery, right? And we are now also find question number 1. R equivalent. Number 2, the current that flows through each resistors. Okay. The same question, the same figures rather, but in this time, we are told that they are connected in what? In parallel. So what do we do here? Let's draw our circuit. For a simple circuit, we can just bring out the battery source. Then we have the first resistor. We have the second resistor. We have the third resistor. Right? Our battery is 120 volts. Here we have 2 ohms. Here we have 6 ohms. Here we have 9 ohms. This is R1, this is R2, this is R3, right? All right. The first thing we have to find is our R equivalent. And we have to recall that R equivalent for a parallel connection is 1 over what? R1 plus what? 1 over what? R2, all to the power of -1. Or we can say R1 plus R2 divided by what? R1, R2 divided by R1 plus what? R2. Right? So any of these formulas can also go. Okay? From here we got this. Is that clear? So let's solve. So our R equivalent becomes, let's analyze with this and see. We have 1 over, what's our R1 here? Okay, we have 3 resistors. So this will be 1 over what? R1 plus 1 over R2 plus 1 over what? R3, all to the power of -1. Right? Okay. All right, so this is our expression here. Okay, or we can simply say this can also be R1 plus, R2 plus, R3. Then we have R1 times R2 times R3. Because by the time we evaluate this, the LCM is R1 times R2 times R3. Then when we evaluate, that will give us R1 plus R2 plus R3, right? But let's make use of this. Let's make use of this, okay? I think that expression I just did is wrong, but let's just use this formula direct. So let's go. So our equivalent will give us 1 over, our R1 is 2 plus 1 over what? Our R2 is 6 plus 1 over 9 to the power of minus 1. Okay, let's check out what will be the LCM here. 9 times 6 times 2. Okay, the LCM between these numbers can be 18, right? 18 divided by 6. Okay, 18 can go as the LCM. Or I always say something. In case you are unable to get the LCM, you can just multiply these values together. So let's go. 9 times 6 times 2 will give us 108. We can also use this as the LCM, right? So divide 108. But if you look at this, what is that lowest number that can divide 2, 6, and 9? I guess it's 18. So 18 can go as the LCM, right? Okay. So when you divide 18 by 2, that will give us 18 divided by 2. We have 9. 9 times 1 is 9 plus divide 18 by 6. 18 divided by 6 will give us 3. 3 times 1 is 3 plus divide 18 by 9. That will give us 2, right? By 9, that will give us 2. Okay, all to the power of minus 1. So our equivalent becomes 9 plus 3, that is 12. 12 plus 2, we have 14. 14 over 18 to the power of minus 1, right? Okay, so the next will give us our equivalent becomes, this sign means inverse, here becomes 18 over what? 14. So divide 18 by 14 will give us about 1.2857 ohms. 1.2857 ohms. That will be our answer there. That will be our answer there. Or we can approximate this to be about 1.29 ohms, right? 1.29 ohms. So this is our RO equivalent. But we are now asked to find the current that flows through each of the resistor. The current that flows through each of the resistor. Now, how do we find the current that flows through each of these resistors? Recall that voltage equals to IR. That is from Ohm's law, right? Ohm's law. If V is equals to IR, that means my current is equals to V over R equivalent, right? Good. So what we do here is that our voltage will give us what? Our voltage here will give us, we have 120 divided by, what's our R equivalent? That will give us 1.29. Let's find the current that flows through the circuit first. Our current will be 120 divided by 1.2857. This will give us about 93.33 ampere. So the current that flows through this circuit is about 93.33 ampere. So let's check this out and see if that will give us the value of the current. So current that flows through each of the resistor will then be, recall, for R1, current that flows through R1 from V equals to IR, current that flows through R1 is 1, which is equals to what? V1 over what? Over R1. But in this case here, we say that since these resistors are connected in parallel, that means the same voltage across them. The voltage drop here is 120. The voltage drop here is 120. Voltage drop here is 120. So I'm saying V is equals to V1 equals to what? V2 equals to what? V3, right? So we have the same voltage drop, but we have different currents. So to find the currents across R1, I'm going to use my V1 over R1. My V1 is same as my V, which is 120. So that will give me 120 divided by R1. What's that R1? R1 is 2. All right. So this will give us about 60 amp. Let's find for that of I2. I2 will be V2 over R2. V2 is also 120. Right? 120 divided by what? By 6. 120 divided by 6 is 20. Okay, is 20 ampere. The next is to find our I3. I3 is V3 over what? R3. The same voltage, we have 120 over what? Over 9. 120 divided by 9 is 13.333 ampere. Now, what do we notice here? The total current that flows through this circuit is simply 93.33 ampere, right? What does that mean? By the time we sum up everything, we sum up I1 plus I2 plus I3, the value should give us 93.33 ampere. That means by the time we sum up everything, the answer must be equals to that. Let's verify. 60 plus 20 plus 13.333 will give us about 93.33 watts ampere. Are you seeing it now? So the sum of all currents here is equals to what? 93.33. What that means is that the current, this current here that flowed through the circuit is, okay, 93. Current here is 93.33 ampere. When the current gets to this junction, it splits. The current that flows through R1 is 60 ampere, right? 60 ampere. When the current gets to this point, it splits as well. It continues and it splits. Here we have our I2. Current here is 20 ampere. 20 ampere. When the current gets to this point, it also splits, right? The current that flows here is what? Is 13.33. So when this current gets to this point, they will all meet at this point. Abi, R1 will continue. I1 will continue. I2 will continue. I3 will also continue. So by the time they get to this point, they will sum up as what again? 93.33. So the concept here is that when resistors are connected in parallel, okay, they have the same voltage drop like we just saw, but different current must pass through the resistors from each of these junction. All right, must have to pass through this resistor. Okay. All right, so let's continue. All right, there is something I want us to look at, which is very important. There's a question we'll need to solve now from your textbook. But before we solve that question, I want us to note that when resistors are connected in series, total resistance will increase. Total resistance will increase. All right. But when resistors are connected in parallel. Okay, total resistance will drop, will decrease. Total resistance will decrease. What does that mean is that series connection increase resistance, it increases it. Why parallel connection decrease resistance? Let me explain that. If, for instance, R1 is given as 2 ohms, and R2 is given as, let's say, 3 ohms, all right? And we are asked to find total resistance in series. Total resistance in series will give us what? R1 plus what? R2, right? We have to just sum up. That will give us 2 plus what? 3 equals to what? 5 ohms, right? Equals to 5 ohms. But if we are to find, this is for series, right? This is for series. If we are to find the same with the same value, but in parallel, it means my R equivalent will be 1 over what? R1 plus what? 1 over what? R2 to the power of minus 1, right? And that will give us 1 over R1 is 2 plus 1 over R2 is 3, all to the power of minus 1. Let's see what will be the result here. Our R equivalent will give us LCM is 6 here. Here we have 2 plus 3, right? Minus 1. Then we are going to have here our equivalent to be equals to 5 over 6 minus 1. So my R equivalent will be equal to 6 over 5, right? Inverse simply means I have to bring up the other number, right? So 6 divided by 5 will give me about 1.2 ohms, right? If you look at this, with the same value, we have 5 in series. With the same value, we have 1.2. So there's a decrease here. There's what here? An increase. So resistor in series increases the resistance. Resistance tends to increase when resistors are connected in what? In series. If I have 2 resistors, R1, R2 in series, okay, end to end, it will definitely increase the resistance like we just saw. If they are connected in what? In parallel, what do you notice? There's a decrease in what? Resistance. 1.2 is lower than what? By 5. Lower than 5. 5 is greater than 1.2. So this means an increase in resistance. This means a decrease in resistance. So note that resistors connected in series leads to increase in resistance, while in parallel leads to a decrease in what? In resistance. So we have a question that says, I have a question here, IMSU, in IMSU textbook, also UNN textbook. UNN textbook. Those of you that attend UNN, this is a textbook. So let's analyze this together. This is a common question in all exams. The question says, a student carrying out an experiment. A student carrying out an experiment to investigate Ohm's law. Required to limit the current flowing through a 10 ohm resistor. The current flowing through a 10 ohms resistor to 20 ampere. when a power supply of 240 volts was connected. How should an auxiliary resistor, resistor be connected in the circuit, and what is the value of its resistance, Okay, let's look at this question here. The question says that a student carrying out an experiment to investigate Ohm's law. When I say investigating Ohm's law, what comes to our mind is what? V equals to what? IR, right? To investigate Ohm's law, required to limit, please mark the word limit. Limit means to reduce, to limit the current flowing through a 10 ohm resistor to 20 ampere. I have a cell, right? And I have a resistor here, okay? This is 10 ohm watts resistor. The current, okay, the voltage source we are told is 240 volts, okay? Then we have a current here. We want to limit the current flowing through this resistor. We want to limit, okay? Then resistor, the current, to limit the current flowing through a resistor, to a 10 ohm resistor to 20 ampere. I want to limit the current to this 20 ampere. So the target current, our target current, the current we need, which is our total current, should be what? 20 watt ampere. That's our target current. When a power supply of 240 volt was connected, that means our total voltage, which is this, is actually 220 volts. So our V is 240 volt rather, is 240 volts. So the current we are targeting, want to limit, possibly maybe the current is more than 20 amp. The question says a student carrying out an experiment to investigate Ohm's law. Required, the aim of the experiment is to limit the current flowing through the 10 ohm resistor to what? To 20 ampere. When a power supply of 240 volt was connected, how should an auxiliary resistor be connected in the circuit? And what is the value of its resistance? When I say auxiliary resistor, meaning we need to add a resistor to support this 10 ohms of resistor. Auxiliary is a support resistor, okay? And for me to reduce, to limit the current flowing through this resistor to 20 ampere, what should we do? I have to increase the resistance. Is that not somebody? If I have a resistor here connected side by side with this, let me give an illustration. Let's say, for example, now I have a bulb. There's a particular amount of current that is permitted to pass through bulbs based on their power rating. There are some bulbs that have 20 watts, right? Some bulbs that the power rating is 40 watts. That means that every of these bulbs have a permissible amount of current, right, that is allowed to pass through them. Now, if a current flowing through these bulbs, okay, let's say the current is greater than the permissible amount of current that is allowed to pass through a bulb is flowing, what do we do to maintain that amount of current that we need? Is by connecting a resistor. So a resistor tends to resist or tends to reduce the opposition to the flow of currents. So what we do here is that we want to limit the current flowing through a 10 ohm resistor to 20 ohm. To limit it, to reduce the current to 20 ohm, that means I have to increase my resistance. It means I have to add a resistor to support the given what? Resistor. This is a given resistor, right? Okay, so let's call this R1. We are told that our R1 is equals to what? Is equals to 10. Okay, now I said this before. Now I asked the question, if I have resistors connected in series and in parallel, which of these will increase the resistance? Is in series, abi? Series connection tends to increase resistance. So for me to limit this, we are saying that we have to increase the resistance, right, of that circuit by adding what? An auxiliary. Auxiliary resistor is an extra resistor we are adding to the circuit just to support, just to aid the original what? Resistor. So by the time we connect this, now let me ask, what do you think will be? Are we going to connect this with the auxiliary in series or in parallel? What increase the resistance is series connection, not parallel what? Connection. So that means that question says, how should an auxiliary and assisting, okay, or resistor be connected in the circuit, and what is the value of its resistance? That means that the answer should be series, right? For me to limit my current, I have to increase the resistance by adding an auxiliary resistor to the 10 ohm resistor. So the first answer is that the connection must be what? In series. Now, number 2 is this. The question has said, what is the value of its resistance? Meaning, what is the value of the auxiliary resistor that should be added to the 10 ohm resistors in order to limit the currents to be what? 20 ampere. So what do we do here is that we have to recall. We have to recall that V, right, is equals to what? IR. Here we are giving our target current to be 20 ohms and our voltage to be what? To be 240. Okay, so what we do is to find the total resistance. From here we can have that our resistance is equals to what? V over I. That will give us our voltage is 240. 240 divided by the given current. 240 is our voltage. What's our given current? Is 20. The current here is 20. So what we have here, 0 can go with 0, 2 here 1, 2 here is 12. So that means my resistance is what? Is 12 ohms. Now what did notice? Resistance increase to 12, but the resistor is what? Is 10 ohms. The given resistor is 10 ohms. So what do we do? If the total resistance has increased, abi, to 12, that question will now be that what will be the value of the auxiliary resistor that will be added to this 10 ohms to give us this 12 ohm resistor? Since we agree that it must be connected in series, abi, let's say I have my auxiliary resistor, let's call it RA, and we are saying that our RO equivalent is 12. In series means we have to add up 10 plus the auxiliary, right? That will give us the total resistance. Since our total resistance is 12, calculated from using the total voltage and the target current, this is taken as the total current that flows, because this is the current we want to limit the circuit to. So this becomes the total current, the current we need, the target current, the required current we are looking for. This becomes what? The voltage given in the circuit. So when you divide the voltage by the total current, that will give us 12 ohms. So that means the resistance tends to increase, of which we have seen that whenever resistance increases, that means the two resistors must be connected in series. So that means to get my auxiliary resistor, what do we do? To get our auxiliary resistor, what do we do? is that since we are connecting them in series, it simply means that our RO equivalent equals to what? RO1 plus what? ROA. Let's call this RO1, this ROA, right? So our RO equivalent is giving us 12 equals to RO1 is 10 plus what's the ROA? Let's call this ROA. So to find ROA, which is the auxiliary resistor, equals to 12 minus what? 10. So the ROA becomes what here? Becomes 2 ohms. So the value of the auxiliary resistor is simply what? 2 ohms. This is very simple. This is very simple. So the value of our ROA that we need to support our RO1 in order to limit the current to 20 ampere is 2 ohms. All right. So let's proceed into next question. Please, if you are following, indicate that you are following. If you are following, indicate in the comment section that you are following. Please, if you are following, indicate that you are following. Let's see an example. We have a question here that says, we are given a circuit. I'm going to draw the circuit and we analyze the circuits together. Consider the circuit below. Calculate the resistance. Consider the circuit below. We are given a simple circuit. Let me just draw. All right. Look at this circuit here. We have our RO1, we have our RO2, we have our RO3. And the question says that the first thing we are asked to find in this circuit is question 1, find the RO equivalent, total resistance. Number 2, the currents flowing through each resistor. Current flowing through each resistor. Number 3, the voltage across each resistor. Voltage across each resistor. Voltage across each resistor. Number 4, power absorbed by each resistor. Power absorbed by each resistor. The 5th one, power delivered by the battery. Powered by the battery. Let's call that PB. Okay, look at this resistor, this circuit. This is a circuit that has 3 resistors. We have RO1, RO2, and RO3. When you look at this resistor, you can see that RO1 and RO2 are in parallel, right? Because there's a junction here. There's another junction here, right? So this and this are in what? In parallel. Then this combination, RO1 and RO2, are in series with this, right? If I'm to resolve this to lie in here, then any value we have here will be in series with this. So the first thing we need to do is to resolve this first in parallel. Okay, this is a circuit, is a complex circuit now. We are moving gradually to complex circuits. So here we have R1, we have R2, we have R3. Okay, let's solve is that. Let's solve. R1 and R2 are already in parallel, right? I hope we know why they're in parallel. If you look at the, I have a node here, I have another node here, right? I have a junction here, right? Okay. So since this and this are separated by junctions and node, so they are said to be in parallel. But if I have a circuit like this, where nothing is separating them, are you seeing this? Okay. This is series arrangement. They are connected end to end, all right? But for this, by the time we move down this way, there's a node here. There's a node here. I have a branch, I have a branch, I have another branch. Okay, there is a junction that's separating the two resistors. So this makes this diagram, this circuit to be what? To be in parallel. So R1 and R2 are in parallel. Then their combination will not be in series with this. So what we do is to resolve. I'm going to say R1 and R2 are in parallel. So since they are in parallel, to find their equivalent, the equivalent of R1 and R2 will now be R4. Because R4. Already we have R1, R2, R3. Once we resolve this in parallel, we're going to call the results R4. The I is R4, okay? So that'll give us 1 over R1 plus 1 over what? R2 minus 1. And that will give us what here? 1 over R1 is 20 plus 1 over what? 5 to the power of minus 1. So R4 becomes, the LCM between 20 and 5 is 20. 20 into 20 is 1. 1 times 1 is 1. Plus 20 into 5 is 4. 4 times 1 is 4. Minus 1, right? Okay. So this will give us what here? 1 plus 5 give us 5 over 20 minus 1. Okay. So at the end of the day, 5 over 20 to the power of minus 1 simply means inverse. I will bring up this 20 on the numerator. This simply means 20 over what? 5, right? 20 over 5. Inverse of 5 over 20 is 20 over 5. So when you divide 20 by 5, our R4 will be 4 ohms, right? 4 ohms resistor. 4 ohm resistor. Okay, so let's proceed. Let's verify this. Okay, 25, 4. Okay, let's go. Now, we have resolved this. Now, the new circuit will then be this, right? This will be the new circuit. Let me minimize my space. This will be the new circuit. We still maintain our 20 volts. These are 20 volts. 20 volts. Our battery is 20 volts. This part is here is positive, right? This is negative. The longest side is positive. The shorter part is what? Negative. The longer part is positive. Shorter part is what? Negative. And currents tend to flow this way, right? Currents flow from the positive terminal of the battery, not from the negative terminal. Electrons flow from the negative terminal, but current must flow from positive what? Terminal. Okay. But after combining this, we have this, right? So I have my plus, I have my minus. Here we have R4. Here maintains what? R3. You know, we combine these two to form R4. So our R4 is 4 ohms, right? 4 ohms. Our R3 is 6 ohms. So R4 and R3 are in series. R4 and R3. Okay, or let me say R3 and R4 are in series. are in series. So by the time we combine them, that will give us RO equivalent, right? And that will be equal to RO3 plus RO4. So our RO equivalent is going to be the sum of these two will give us 6 plus 4, which is equals to 10 ohms, right? Okay, we can decide to draw our new circuit, or we can even leave it, but let me just draw for the sake of this class. This becomes my new circuit. Here we have RO equivalent to be 10 ohms. Here we have our battery source as 20 volts. This is the new circuit. But the question says find the RO equivalent, of which we have done. Okay, number 2 says find the current that flows through each of the resistors. Current that flows through each of the resistors. Look at this. We say that for resistors in series, we say the same current flows through. If you are looking for a current, we have to start from the last part. We have to start from here. Okay? You don't solve with current from here. You start with the last part, the last resolution. So our RO equivalent is 10 ohms, right? The first thing we need to find is the current first. Let's find current. Recall that V equals to what? IR. So here, my I will be V over what? R. Our voltage is 20 volts divided by our RO equivalent over RO equivalent. What's the RO equivalent? We got 10. So this will give us what here? 2 amp. So the current that flows through the circuit is actually 2 ampere. What do you notice here? 2 ampere of current. Once they get to this point, when these 2 ampere get to this point, it will split. One will enter here. I have current that enters here as I1, right? I have the one that enters here as what? I2. So I1 plus I2 give us what? I what here? I3. Are you there? So that means RO1 and RO2 are in parallel, but their combination is in series with what? RO3. So don't forget that for series connection, the same current flows through. So that means that the current that flows through RO3 is still the same current as what? 2 ampere. But the current that flows through RO1 and RO2 are not equals to what? 2A. Because there must be a split of current here. This is the junction where current tends to split. So along this side, current that flows through RO1 is what? I1. Along this side here, current that flows through this resistor is what? Is I2. So you can notice that there's a current passing through this junction, right? Which is what? I1. There's one passing through, leaving, as if it's leaving this junction, as what? I2. There's one passing through our resistor, which is what? I3. So the current, RO3, look at this. RO3 is in series with combination of what? Of RO1 and what? RO2. RO3 is in series with this combination. When we combine this, that gives us RO4, right? That means that these two are in series. The combination of these two gave us what? 4 ohms resistor. So the current that flows through RO3 must be the same current that flows through what? RO4. So the current that flows through this circuit is 2 ampere. It's the same current that flows through what? RO4 and what? RO3. So to solve for RO3 is very simple. We just say find the current that flows through each of these resistors. Sorry, 20 volts. So let's go let's find out I3 first. I3 we know is the same current, which is what? Which is 2 amp, right? Current that flows through RO3 is what? Is 2 ampere. See it here, is 2 ampere. Okay, let me say for RO3. For RO3, so my I3 is 2 ampere. Now let's look at this. We have a parallel connection here, and their total resistance is what? Is RO4. But we want to find the current that flows through R1 and what? R2. For R1, current that flows through R1 is I1. And that current can be gotten by multiplying total current by R1 and R2 are in what? Are in parallel. So the formula to find my I1, okay, will be total current times R2 divided by R1 plus what? Plus R2. To find the current that passes through I2, I will use I2, which is equals to what? Total current times R1 over what? R1 plus what? Plus R2. Please take note of this formula. Current that flows through R1 is I1. And that current is equals to what? Current, which is our I. The total current here is 2 ampere, right? Times R2 over R1 plus R2. When it comes to capacitors in parallel, it's not the same thing. In series and in parallel, not the same thing, right? Good. For capacitors in parallel, we are talking about charges. That is, that different charges flows through a given circuit. If I'm to find, let's say, for example, if this is a capacitor, this is a capacitor, I'm not to find the charge that flows through the first capacitor. Formula will now be charge 1 equals to what? Total charge times C1 over what? C1 plus what? C2. To find that of Q2, formula will be C total times what? C2 over what? C1 plus what? C2. This for capacitor. But when it comes to resistor, the reverse is the case. For capacitor, for resistors, okay, in what? In parallel. To find the current that flows through R1, formula says I1 equals to current times R2 over R1 plus what? R2. Okay, let's solve for this first. Then we'll solve for I2. So let's go. So for I1, that will give us our total current is 2. Our R2 is 5. Don't forget R2 is 5, right? It's 5 divided by R1 is 20. 20 plus 5. This will give us 2 times 5 divided by 25. This will give us 2 times 5 is 10. 10 divided by 25. Please, if you are following, indicate that you are following. By the time we divide 10 by 25, the result is 0.4. We have 0.4 ampere. Okay. Look at this. The total current that flows through here is 2 ampere. Already we have gotten our I1, Abi. So since we are saying that these two are in what? In parallel, it means that along R1, 0.4 ampere current flows through this. If the total current is 2 ampere, current split, if 0.4 flows through here, what do you think will be the current that flows through R2? It's simply by subtracting 0.4 from what? From 2. Because this current is splitting. We have 2 ampere, 0.4 flows through here. What will flow through here will now be what? 2 minus 0.4, which is about 1.6. Right? So if 0.4 comes down, 1.6 comes down, that will sum up here as what? 2 ampere. That's why we are saying that current that flows through I3 is same as what? 2 ampere. Because R3 is in series with this. In series, the same current must flow. Current here must be 2 ampere in total. Current here must be what? 2 ampere. Because R3 and these two combinations are in series. So let's see that of I2. What would be that of I2? Okay, that of I2. Let me clean from here. I2 will then be I times, from this formula, the formula is going to be R1 over R1 plus what? R2. So my I2 will be, our I is 2 times R1 is 20 divided by R1 plus R2 will give us 20 plus 5. This will give us 2 times 20 over 25, right? This will give us 2 times 20 is 40. We're going to have 40 over 25. So when you divide 40 by 25, the answer is 1.6. Are you seeing that the sum of I1 and I2 is equals to what? 2 ampere. That means along my R1 we have 0.4 ampere. Along here we have 1.6 watt ampere. So when you add up this sum, we're going to have what here? 2 ampere flowing through what? R3. Okay, so the current here is 1.6. Alternatively, since we are saying that 0.4 flows through R1, to get our I2, just subtract 0.4 from what? 2 ampere. That will give us 1.6. Are you there? The next question says, calculate the power delivered by each resistors. The power delivered by each resistors. Okay. Let's solve for the power by each resistor. Before we solve for the power by each resistor, let's indicate our values. Our I1, we have already solved as 0.4 ampere. Our I2, we solve as 1.6 ampere. Our I3, the value is 2 ampere because the value of the current that flows through here is 2 ampere, right? Okay, so let's also note that our voltage potential difference is given as 20 volts, right? 20 volts. All right. Okay, I think the next question says find the potential drop or PD across each of the resistor. Okay, the next is to find PD. PD at R1. From Ohm's law, V equals to what? IR. V equals to IR. It means to find my PD at R1, I'm going to use V1 equals to I1 R1. So my I1 is 0.4 times R1 is 20 times 20. Let's see what we are going to have here. 0.4 times 20 will give me 8 volts. So for V2 is I2 R2. I2 is 1.6 times our R2 is 5. Multiply 1.6 by 5, the result should be 8. 1.6 times 5, the result is also 8 volts. Why do we have the same value? Because R1 and R2 are in parallel. And I will say that in parallel, they must have the same potential difference, the same potential drop, PD, across resistors connected in parallel. So the potential drop here must be the same with the potential drop here, or PD in R1 must be equal to PD in R2. But let's find the PD in R3. Okay, PD in R3. All right. We have seen PD at R1 and what? R2. Let's find PD at R3. PD at R3 is going to give us V3 equals to what? I3 R3. Our I3 is 2 ampere times our R3 is 6. So the result will give us what here? 12 volts. So let's verify. The sum of all voltage in each of these resistors must be equal to 20. These are 20 volts, right? Now, the potential drop here is 8. When you add up your 8 volts plus 12 volts is equal to what? 20 volts. Are you saying that the sum of all PD must be equal to what? To 20. Because we say that in series connection, R3 is in series with R1 and R2. Then in series connection, we're going to add up their voltage, right? So it means that voltage here plus voltage here must be equal to total voltage. So the voltage along R3 is 12. Voltage along R1 and R2 is 8. So that 8 plus 12 is equal to 20. So this shows that our answer is 100% accurate. The next question is to find power absorbed by each resistor. Power absorbed by each resistor. Power absorbed by each resistor. Okay, power absorbed by each resistor. Power. For that of R1, power absorbed by R1 is going to give us P equals to I squared. Formula for power says I squared R, right? Power can also be given as IV or IV, right? Or power equals to V squared over R, right? Any of this can actually work for power. So let's make use of the first formula. P is equals to I square R. For R1, P equals to what? I square what? R. So power absorbed by resistor 1 will give us P1 equals to I1 square times R1. So my P1 will give us I1. Our I1 is 0.4. So 0.4 all squared times R1, which is 20. Let's verify. That will give us 0.4, 0.4. Okay, 0.16 times 20. Here we have 3.2. Our P1 here is 3.2. Okay, watts. Let's find the power absorbed by R2. That will give me P2 equals to I2 squared R2. So for P2, my I2 will be, my I2, okay, our I2 is 1.6. 1.6 all squared times R2. R2 is 5. So 1.6 squared times 5 is about 12.8. 12.8 watts. 12.8 watts. The next is to find power absorbed by resistor 3. Power absorbed by resistor 3 by R3. For R3, that will give us P3 equals to what? I squared 3 R3, right? Okay. So P3 becomes what here? Our I3 is 2 squared times our R3 is actually 6. So here we have 4 times 6. Please, if you are following, indicate that you are following. If you are following, indicate that you are following. So here our P3 becomes, I guess that should be 24 watts. The last question then says that what is the power delivered by the battery? Last question says power delivered by the battery. By the battery, it simply means I'm going to use the battery. So for me, I can say P is equals to what here? IV. So here we have P equals to total current that flows through the circuit. Total current here is actually 2 ampere, right? 2 amp. So we have 2 times our voltage, our potential difference. Our voltage is what? Is 20. So when you multiply 2 by 20, that will give us 40 watts. 40 watts. Alternatively, another way we can find our power, alternatively, another way we can find the power delivered by the battery. When I say the battery, that means I'll multiply the current that flows from the battery times the potential difference or the voltage of the battery. The current that flows is 2 times 20 from the formula P equals to IV, right? And that way, alternatively, is Power divided by the battery can also be given as P total equals to P1 plus what? P2 plus what? P3. Meaning the power absorbed by resistor 1 by R1 is our P1, which is 3.2, plus power absorbed by what? P2, which is 12.8, plus power absorbed by R3, which is 24. Let's add up this and see. 3.2 plus 12.8 plus 24. This will give us 40. So total power is still what? 40 watts. So if you are confused, you can just sum up all the power absorbed by each of the resistors. We give us the power delivered by the battery. All right. So let's see another example. All right, guys. So more examples than we. Please, I want you guys to comment. If you are following, comment. If you are following, comment. And let's keep on sharing the link rather, to our various groups. All right. Keep on sharing the link. 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 Okay, let's see another circuit. A simple circuit. We are given a circuit like this. We are given a circuit like this, and we are asked to find number one, our equivalence. Number two, the current that flows through the circuit. Number three, the current that flows through each resistor. Right? Number four, we also find, okay, so I just have to put on the lights. All right, so sorry for the little break. I have to put on the lights. Now we're given a simple circuit like this, and we have to find our arrow equivalent, current that flows through the circuit. All right, we have to find current that flows through each of the resistors, R1 and R2. Then we also have to find power absorbed by each resistor. Then number four, power delivered by the battery. Okay. Look at this. This is a very simple circuit. Here we are given two resistors connected in series because we have a junction, we have a node that separates the two resistors. So what we do here is to find our R equivalent, right? Our equivalent is going to give us 1 over R1 plus 1 over R2 to the power of -1, right? Okay, so let's solve for our equivalents. These two are in parallel, so this is the formula that will be used to find their equivalent resistance. So our equivalent will be 1 over, our R1 is 4 plus 1 over 6, right? Okay, to the power of minus 1, to the power of minus 1. So yeah, the LCM between 4 and 6, our equivalent is going to give us 12, right? Our LCM is 12. 12 into 4 is 3. 3 times 1 is 3. Plus 12 into 6 is 2. 2 times 1 is 2. Minus 1, right? Okay. LCM is 12. 12 into 4 will give us 3. So 3 multiplied by 1 is 3. 12 into 6 is 2. 2 times 1 is 2. So we have our equivalent to be 5 over 12 minus 1. Inverse of this will give us 12 over 5. And by the time we divide 12 by 5, let's divide 12 by 5. We have 2.4, right? We have 2.4 ohms. So our equivalent here is 2.4 ohms, right? Okay. So the next is to find the total currents, IT, I total, that flows through this circuit. Because there's a splitting here. When this current flows from this battery, it will split. I1 will flow through here. Then here we have our I2 that flows through this. So the sum of these currents we meet at this point, right, to give us our I total. So let's find our total current from Ohm's law. From V equals to what? IR. So total current will give us V over our equivalent. So our voltage is 12. 12 divided by our equivalent is about 2.4. About 2.4. So 12 divided by 2.4 is about 4.8. Sorry, about 5. I think so. 12 divided by 2.4 is 5. Okay. 5 ampere. 5 ampere. All right. So the next is to find the current across each resistor. We have R1 and R2 arranged in parallel. I've already taught us how to find current that flows in a resistor in parallel. So to find this, current that flows to I1 is I total times R2 over what? R1 plus what? R2. Don't forget this. Okay, R2. This will give us our I1 is equals to our I total is 5. 5 times our R2. R2 is 6. 6 divided by, then we have 4 plus 6, right? We have 4 plus 6. This will give us our I1 equals to 5 times 6 over what? 10. So here we have 5 times 6 is 30. Divided by 10 give us 3 amp. So our I1 is 3 ampere. So for that of I2, that will give us I2 equals to I times R2 divided by, R1 rather, divided by R1 plus what? R2. So I2 becomes, our total current is 5 times our R1 will then be 4 divided by 4 plus 6, all equals to, here we have over 1. 5 times 4 is 20. 20 divided by 10. So when you divide that, that will give us 2 ampere. What do you notice here? The current that flows through I1 and I2 are not the same, but the sum of this current must be equal to what? 5 ampere. Total current is what? It's 5, right? Total current is 5 amp. So current that flows through I1 is what? I1 is 3 ampere. Here we have 3 ampere current. Here we have 2 ampere current. when this current emerges from here, when this emerges, 2 ampere flows through. So at this point, they will sum up to be what? To be 5 ampere. So the sum of all currents in this circuit must be equal to 5 ampere. Okay, we have seen, we have solved this, we have solved this, we have solved this. The next thing we did here, the next thing is here is what? Power absorbed by each resistor, of which I've already taught us how to find, right? Before we go into that, we have to bring out our I1 is 3 ampere, our I2 is 2 ampere, our total current is 5 ampere, our voltage is 12 volts. So let's find power absorbed by each resistor. Power absorbed by each resistor. To find the power absorbed by each resistor, power by each resistor. To find P1, P1 will give us I1 squared R1, right? So P1 is equals to I1 is 3 ampere. So 3 squared times R1 is 4. This will give us about 9 times 4. And that will give us about 9 times 4 is 36. So we have P1 is 36 watts. P1 is 36 watts. The next is to find power absorbed by R2. Power absorbed by R2. Power absorbed by R2. That will give us P2 equals to what? I2 R. So power absorbed by R2 will give us P2, or I2 is 2 ampere. So we have 2 squared times our resistor. Here is 6. So we have 4 times 6. So the answer becomes 24. All right. 24 watts. That is the answer. Then the next one says power delivered by the battery. Power delivered by the battery is equals to, when we use P equals to what? IV. So our P equals to total current times total voltage. Total current is 5 times our total voltage, which is 12. So 12 times 5 times 5, which is 60. So total power absorbed is 60 watts. I also say that to find the power delivered by the battery, we can sum up the power absorbed by R1 and what R2. That will give us total watt power. Meaning by the time we add up P1 plus P2, our P1 is 36 plus 24. The result will give us 60 watts, right? Okay. Please, if you are following, indicate that you are following. If you are following, indicate that you are following. All right. If you are following, indicate that you are following. All right, guys. So we are supposed to go into Kirchhoff laws today, but that will be tomorrow. But I'm going to explain a little about Kirchhoffs. Then in tomorrow's class, which is Sunday, we'll continue with Kirchhoffs. Then we analyze some circuits. There are some certain circuits that we cannot analyze just like we did. We have some complex circuits where we have more than 2 independent voltage source. Like we can have a voltage source here, we can have another voltage source here. Are you there? We can have a voltage source here and that voltage source here. Where we have more than 2 or more than 1 independent voltage source. Okay? We call such kind of circuit a complex circuit where we have more than 2 loops. We have a loop, we have another loop, all right? We have multiple resistors, okay? we call such kind of circuit a complex circuit. Ohm's law is actually limited. Ohm's law is limited in the sense that Ohm's law can only be applied for a simple circuit, just like we did. But for complex circuit, where we have more than two independent voltage source, more than two loops, more than two loops, more than two voltage source, multiple resistors. All right, such kind of circuit are called what? Are called complex circuits. So we cannot use Ohm's law to analyze such kind of circuits. We have to use what we call Kirchhoff's. Okay, Kirchhoff's law. But I'm not going to go into Kirchhoff's law today. Tomorrow, by either 4 p.m. or 5 p.m. after church service, we shall be looking at Kirchhoff's law. Our next topic is going to be on this, Kirchhoff's circuit law. Circuit law. Circuit law. And that class will be tomorrow, which is on Sunday, right? On Sunday by 5 p.m. The same time for today's class. We shall look at how to analyze a complex circuit. Okay. And Kirchhoff's have two fundamental laws. There are some certain terms we shall look at. We look at the two laws of Kirchhoff's. We have the Kirchhoff's current law and the Kirchhoff's voltage law. The Kirchhoff current law talks about the total current that enters through a junction in a particular circuit is equal to the current that leaves that same junction. But the voltage law is saying that the total voltage in a complex circuit, right, must be equal to 0. And we shall look at how to solve for different currents in the complex circuit by using simultaneous equation. So it's a class that you cannot afford to miss. Inform your friends, inform your colleague. Tomorrow being Sunday by 5 p.m., we shall be looking at Kirchhoff's circuit law. Then after Kirchhoff's circuit law, we then move into what we call the instruments used in DC, like the meter bridge, the potentiometer, how to convert the shunt resistors, the multipliers, and all of that. Those aspects falls under the instruments. But for now, for tomorrow's class, the only thing we shall be dealing with is Kirchhoff's circuit law. We shall look at the first and the second law of Kirchhoff's. So please, if you have any question, you can drop those questions in the comment section and ensure that you save this video. You save this video for reference purpose. You can always ask questions. My phone number, for those of you who don't really know me, my phone number is this: 09063 111 961. My name is EMI-BRAIN. All right, EMI-BRAIN. Okay, if you want to join our WhatsApp platform, you can always reach out to me. We add you up to our WhatsApp group. We have a WhatsApp group for all science students. All right, so see you in class tomorrow by 5 p.m. Don't miss this class. Don't miss this class. After the class, I'm going to lock the lecture in a way that it will be a private class. Nobody can access it. But there's some secret I want to show us tomorrow on how to analyze a complex circuit. This secret is not in your textbook. It's personal to me. So please make sure you are here in this live class tomorrow. So see you tomorrow by this time, 5 p.m. All right. Thank you so much.